Today is continuing with these sailors. Good. If you wonder what's going on here, this shows you what kind of morning I've had. My purple pen ran out, and I found a blue pen, which then ran out, and then I had to find another purple pen to continue. So there's a weird color transitioning going on here. There is a ton of stuff written down here. I'll just chat a few minutes, so if any of you want to copy it, that's fine. If not, why don't you just watch the video sometime and pause it? You need to have all this data written down somewhere. It's just one of those things you can't, unless you're fortunate enough to have a photographic memory. We need to write these things down, but essentially we're estimating the value for the difference in two means. And this stuff here is basically how you would go about it by hand. Even although typically we wouldn't do it by hand, we still need to know how to do it by hand. So you get an idea of what the software that you're using to do it is about. So as I say, I'm just going to talk through this. You can write down what you want or just listen. This here is how you calculate the standard error for the difference in two samples. So you're going to have two different populations, and you collect a sample from the first lot and a sample from the second lot. And this is the standard error. It's the square root of S1 squared over N1, S2 squared over N2. S1 is the standard deviation of the first sample, and this is the second sample. And then that's the key number. That's the guy that kind of does all the good stuff. If you want to find then a confidence interval, which is this is essentially all about, if you decide to use the empirical rule, right, 6 to 8, 95, 99.7. So if you see a question phrased either using the empirical rule or I don't know what phrase they might use, the approximate rule, it's another term I think I've seen. Then a 6 to 8 is the difference in the means plus one standard error, two standard, whoops, did I notice that? Two standard errors or three standard errors. Actually, isn't that formula so much similar to every other version that you could probably figure out if I'd never told you? Right. 6 to 8 is 1 plus or minus 1. There we go, my pen was running out when I did that. Plus or minus 2 gets you 95, and plus or minus 3 gets you 99.7. Now, as long as your data is normal, so if the question talks about the populations came from a normal distribution kind of thing, then let's proofread this. There we go. If you want to get a 90, a 95, or a 99, that's the typical numbers. Same formula, same guy. Only difference is 1.645 for 90, 1.96 for 95, and 2.58 for 99. And again, you could probably guess these, aren't they, the same kind of things that you used when you were doing the difference between two proportions, right? Very similar. And then we've got some stuff over here, which I'll come back to. So for completeness sake, I'm going to do a question where we use this. I'm going to do a question where we use that. And then we'll move on to t-distributions and salt. So let's assume that I'm staring over here at my screen. So they have males in this story. It's a version of question 1. Right, so this is males, and their average height is 70 inches. And the standard deviation is 2.9. For females, it's 65. And standard deviation for females is 2.4. And the population, the sample size for both of these is 9. Now, there are rules about what you can and cannot do. 9 is atrociously small, but as long as the data was normal, right, the populations were normal, you can get away with tiny sample sizes. So we'll assume that this is one of those situations. And from all of this information, we're going to calculate, for instance, question A, we're going to calculate the standard error. And that's where the S1 thingy and the S2 thingy kick in. So in this case, it's going to be a 2.9 squared divided by 9 and a 2.4 squared also divided by 9. I'll kick over here, clear that out of the way. And the square root then, 2.9 squared divided by 9 plus 2.4 squared also divided by 9. And the answer to 2 decimal places is 1.25. And that's basically how you do that. If they ask you for the, well, basically, what would be the difference between the two? And that one's almost hardly worth saying. It would be 5. Guess the units are inches. And let's suppose we wanted to use the empirical rule. I'll make that part C. And I want to use the empirical rule to do a 99% confidence interval. Check if they had any of their own. No, that one didn't do as much as that. Well, that's going to be the difference in the means plus or minus 3 standard errors. And here it's, well, we've actually done that, it's 5. Plus or minus 3 times 1.25. In this case, what do I get? 3.75, that's 1.25, 5, 3.75 is 8.75. So the range, right, the confidence interval, a 95% one, for the difference between these two populations, the males on this side and the females on this side, ends up being these numbers. It's not uncommon. Right. Okay, it's not uncommon for this to finish with, is there enough evidence to prove that one is bigger than the other, right? Or less than the other. Every single number here is positive, agreed? Every number in this interval. So it's saying if you take a male height and you subtract a typical female height, the difference is a positive number, somewhere between 1 and 9 inches, right? What that tells me is that there's evidence statistically, right, that males, the average, is more than females. So the average height of a male is more than the average height of a female. Are we cool with that conclusion based on what we see here, right? Now, it could happen that every single number here was negative. There's 3 things that can happen. That's the first one, right? It's all positive. If they're all positive, the first thing is bigger than the second thing. If they're all negative, what do you conclude in that situation?
Females would be greater than males.
Right? Or males will be less than females is equally correct, right? And if it contains 0, right? So it's a negative this, comma, a positive that, right? If it contains 0, inconclusive, right? We don't have evidence either way. And that's a very common, final step in the process. Okay, I've got the difference between them. What can that tell me? In this case, if I was really being nitpicky, couldn't I say that not only are males taller than females, but on average, aren't they about 1 inch taller, or at least 1 inch taller? Right, because all these numbers are bigger than 1. And that would be an example of using the empirical rule. Going to do one using this one. Now, in this case, we are assuming that the data is also normal, but we want to do a slightly more accurate version of that answer. Yeah. Let's see which one I can use that can do that. Okay. This is version question 3. In this case, a sample of 30, oh God, would you believe people do this? It's men against women again. They don't seem to have a lot of imagination. But anyway, they took a sample of 37 men and they found in centimeters that their average head circumference, you know, you put a tape around the top of your forehead, right, and you measure it, was 57 centimeters, and that the standard deviation was 2.2. So I think we're going to try and prove that men have bigger heads than women, to which probably the females in this class would agree with that very sexist comment. Wait a minute, can it be sexist if you insult males, or it's only sexist if you insult females?
I have no idea.
Huh. Probably. Right. N2. Right, what do they know about the women? Because they have no imagination in this question, there's 37 of them, right? There's no reason that's the same number, right? There is no reason at all. Could be 220 if you wanted, it wouldn't change anything. And they happen to have an average of a little bit less. And the standard deviation in this case is again 2.2 centimeters. Okay, that's basically the data that we're going to work with. And we're going to calculate the usual types of things. Going to calculate a standard error and a difference in the means and a confidence interval, but no conclusions. So if you take the difference in the two, we find that they differ by 1.5 centimeters. Okay. If we calculate the standard error, it's basically going to be that guy squared over 37 plus this guy squared over 37. That shouldn't be that interesting either, but let's see. Square root of 2.2 squared divided by 37 plus 2.2 squared divided by 37. And the answer, what do they want to? 1 decimal place is 0.5. And they want a 95% confidence interval. And since we're using this information, it's going to be the difference in the means plus or minus 1.96 times the standard error. The difference is 1.5, give or take 1.96 times 0.5. This is 1.5, give or take. I should be able to do that. What's that, half of that? 0.98, which comes out to be 0.52 and could be as high as 2.48. And there's our 95% 5% confidence interval for the difference in circumference of heads. Would you agree this is evidence that men's heads are bigger than women's? If they'd switched places, wouldn't everything here be kind of negative? In the rows, that would be negative 0.5, and these numbers would have been negative, and that would have been evidence that women's heads are smaller than men's, right? You can think of things in two directions. Are we comfortable with this process, whether use empirical or use that? So I don't need to do any more of this, right? Good, because you've probably seen variations of a theme for a long time. So let's move on to the student t distribution guy. When you should use it. Well, I'm going to 3 first. If you're collecting data and there's errors likely to be in it. Now, you're measuring heights and circumferences and weights of things, right? And sometimes you're not going to get very good data. Suppose you're out in the field and you're finding out about the weights of birds, right? You're analysing their length, their weights, their wingspan, right? You're collecting data. Maybe to find out what the health of the population of this particular type of bird is. Can you imagine that trying to weigh a bird isn't going to be very accurate? They're either very light or they don't like being weighed, right? So not the best example I can think of, but you know, and when you're out in the field, how do you measure it? You measure it with a tape, right? Would you agree if you gave me to measure a distance and I got Mark to measure it, isn't there a chance that my answer and your answer are a couple of percent out? Because, you know, where does it start? Where does it finish? So if there's errors, or you're just not sure, or you just want to be darn safe that if you make a conclusion that you feel really comfortable with it, you should use a t-distribution. If you know for sure, or you suspect that the population that you're collecting the data, technically, in this case, it's the populations you're collecting the data from, is not symmetric, right? That you know it's very skewed left, it's got 2 bumps in it, it's just weird looking data. You should be using the t-distribution again. And small data sizes, even although, and we've done it, didn't we use a sample sizing 9 and I think it was a 37, right? It's safer if the population size is less than or equal to 30 that you use the t-distribution. And the reason for that is that it's safer. Because what happens is that when you use a t-distribution, the interval that you generate at the end will be bigger than it would have been if you'd used the stuff we did at the start of today, right? Now, because that interval is bigger, if I say I'm 90% sure and the interval is bigger, would you agree that I'd be more likely to be true, right? Because the bigger the interval, right, the more likely the answer is somewhere in that interval, right? So that's kind of the way this is going to work. Here is the formula that they use to calculate the confidence interval. And it uses a thing called the t-multiplier, this funny little t asterisk, t star here. It's the difference in the means plus or minus that guy standard error. Isn't the only difference, if you look at every formula that we've got here, isn't the only difference how much you multiply the standard error by? And in the t-distribution, this number isn't fixed. You know, if you're doing a 95, it's not always 1.96 or 2. This number, this thing called the multiplier, and that's the first thing we're going to do. We're going to show you how to use it in SALT. Depends on 2 things, right? It depends on the size of your data. It's called the degrees of freedom. And I know it's a bit weird, but you subtract 1 from your data size, and that's called the degrees of freedom, n-1. And it also depends on the confidence interval. So what I'm going to do right now is just get in practice at finding the multiplier. Okay. Give me a number between 1 and 10. Anybody, just share it out.
7.
7. Okay. So that makes degrees of freedom 6. Okay, give me a confidence interval you want. 90, 95, whatever. You can even pick 92 if you felt like it. Give me a
90.
confident 90. So we are going to find that magic guy, right? This fella, based on this stuff here, right? So here goes. The T distribution, even if the data came from weird, non-symmetric looking stuff, the T distribution is just like the normal. It's just a bit wider and flatter, right? And the middle is 0, just like a T-score, a normal distribution, a Z-score. And we want a guy such that this fella in the middle is 90%. So I'm just taking you through the process, right? Imagine I did that equally. Now, because that's 90, would you agree that these two ends make up the other 10%? And that makes this end 5%, and it makes this end 5%. Still with me? And since I want this one to be 5 and this one to be 5, as a decimal, that means I want these guys to be 0.05. Okay, let's go hunting for a magic multiplier. So, just going to hit that use salt button. And, oops. There we go. So maybe shrink this a little bit because I want to see the whole shape. There. That guy there right now is the normal distribution. But if I kick it over to the T distribution, do you see it's T distribution now? The degrees of freedom was 7. So you put 7 in there. Agreed? Now, this little guy down here, shouldn't he be, well, darn it, shouldn't he be 0.05? Remember my little picture, 0.05? And that one's already set up. So see this number here? That's your T. Your magic multiplier is, don't worry about the negative, because that's just because it's on that side. It's 1.8946.
I have a question.
Yes.
How do you find degrees of freedom again?
You take one away from your combined sample size. So if you have 40 women and 20 men, the combined sample size there is 60, and then you take one away from it, 59. Right? Make sense? Okay. Let's suppose I'd like a 99%, yeah, 99%, right? Then isn't there only 1% left on each side? Half that, you get 0.05. And you see that this now has turned into a 3 point, I would call that 3.5, wouldn't you? If you rounded it off. Are we okay with how you get the multiplier?
So I have a question.
Yes, Tanya.
The degrees of freedom, you said it's the sample minus 1, right?
It combined sample minus 1, yes.
Okay, because so wouldn't that be 6 for this question?
That is correct.
Okay, just making sure I'm not off here. Thank you.
No, you're not. I've got the number written down, but of course, that requires me.
Okay, I was following the rest. I just wasn't sure about the degrees of freedom.
No, I'm glad you caught it. 9, 4. Right. Okay, let's go back and get that guy or use him now. So that is the fella. Now, if I wanted to use him, wouldn't I just say difference in means plus or minus 1.94 standard errors? You see, the only thing that would change in my formula is that this thing, my finger the multiplier, won't that change depending on data size and so on? Right. Okay, let's try and put that together as a do it by hand question. And then hopefully we can then do salt all the time. So I'm not going to do males and females because we've done far too many of those. So I'm going to make up my own question to kind of go through this process. So we're going to have two populations. Okay, population one are going to be old people and young people. And I'm describing young people because of my age is anybody who's less than 25, less than or equal to, and old people are basically people older than 25. So you might want to have different labels for them, but that's how I'm going to describe it. And we asked the old and the young people, where we collected data on my group of old and young people, and we found out that in the old group, that their average weight was 195, and that I took a sample of 100 to get that, and that the standard deviation was 15. And the younger group, theirs was 185, and I took a sample of 90 of those, and that the standard deviation for them was 10. So I'm collecting this data because I think old people are fat compared to young people.
Wait,
Shouldn't
X bar be the smaller number for both of them?
Should X bar be the smaller number for both of them?
Yeah, because it's a sample of an entire group, so wouldn't X bar be 100 out of 195?
Oh, this is the average weight of old people.
Oh, okay.
Right, it's not a proportion thing, if that's what you're getting at. Right. So the average weight of old people is 195 pounds. The average weight of the young people was 185. So looking at that, do you think I've got some evidence that old people are heavier, fatter than young people, if this was true data? Right. So we'd set up kind of all the information that we need. Well, I know I'm going to have to find that, right? And that's 195 take away 185. So there looks like there's a difference of £10, but couldn't that just be variation randomness? Could happen. I need to know the standard error. And we are talking about a particular kind of standard error. And the formula that I'm writing down here is the not pooled one, right, where each one is totally separate. And that's really the only one you want to worry about if you're ever going to do it by hand. If you do not know whether or not you should pull the data together, then just don't. It's just safer not to. To pull the data, you have to make some assumptions that are pretty hard to prove or even justify. You have to prove that both populations have essentially the same standard deviation, or darn close to it, to make no difference, right? And you also have to assume that both populations are basically the same shape. So they can both be skewed right, both can be skewed left, but you can't have one skewed left and the other skewed right, right? Now, those assumptions are very difficult to know. I mean, if I went and said, I'm out in the field and I'm collecting ducks, and I want to find out, what ducks weigh and height and all that thing, I don't know if ducks are normally are skewed to the left or skewed to the right. Who knows those kind of things, right? So just don't pull your data. It's the safest bet. In this case, it is going to be 15 squared out over 100 plus 10 squared out of 90. So I would go square root of 15 squared divided by 100 plus 10 squared divided by 90 and about 1.8. And the only other thing I need is that guy, right? The multiplier. Okay, so you want a 90, a 92, a 97, a 99. Let's do a 99, eh? So you put a little 99 there. And, oh, I need degrees of freedom. Right, if you the combined data size, would you agree it's 190? Now you take one away from it, which is 189. And hopefully because I've only got that, I won't write the wrong number down. So this fella, you have to kind of do salt. Technically, you don't need to do salt. Do you know you can get a book with these numbers in it and you just look it up? You know, 189, read along, 90%, whatever it is you're looking for. But we're going to use salt for that. And we should come up, hopefully, with the data. So it's degrees of freedom are 189. If I wanted a 99%, doesn't that leave 1% either side? And half of 1% is a half a percent, and a half a percent is 0.05 as a decimal. And so the number I want is what, 2.6? Oh, looks good. And that is the only bit that salt really takes part of right now. So we got all the features, all the data here. So a 99% confidence interval. It's going to be the difference between the two means, plus or minus the magic guy, 2.6 standard errors. And this guy was, where is it, 10, plus or minus 2.6 times a 1.8, and this is 10 plus or minus, here we go, 2.6 times 1.8, so that's about 4.68, so that's at 5.32 or 14.68, and yes, based on that confidence interval, old people are fatter than young people. Sounds good? You know, that's an awful lot of number crunching. Wouldn't it be nice if salt would just do the whole damn thing for us? Right. Well, let's do it. So, pick a question. Give me a second to kind of get themselves organized. Hide that one. Okay. So, this is version question 8. In a research study, volunteers, oh, not the cold one, I'm bored with the cold one. Question 9 is another cold one. Oh, come on. Question 10 is another. Do they have any blinking imagination? Okay. Let's do people's feet. At least it's not cold and taking zinc. So question 11, the foot length of a random sample of 20. You know, if I ever get to meet the guy who wrote this book, and guy could be male or female, I don't know what the person is, I'm going to ask him, what's his thing about colds and measuring men and women? I mean, there's a lot of other things out there, isn't there, that you could collect data on, not just those things. But Anyway, we got that out of my system. This is feet length. A random sample is 72 men. And the mean was 28 centimeters. And the standard deviation was 2.9. 112 women. Well, at least it's not the same number anymore. And they found out what their foot length. And for women, it's 25. So we've just finished proving that men have bigger heads than women. Now we're going to prove that they get bigger feet than women. I suspect. And the standard deviation is 2.9. Oh, should have read more. They actually told you what the standard error is, and well, I'll pretend they didn't, right? So in this question, we are now going to create a 95% confidence interval. And we're going to do the whole thing with salt. It wasn't till I scrolled down that I saw that they'd actually told you the numbers, which they hadn't, but whatever. And where are we? We're here. Okay. So this right now is in a heading called distribution calculations. If you move over to the one called inferential statistics, this is where you'll do all the stuff we're going to do, right? If you want SALT to build a confidence interval, whatever it is, inferential statistics. Now you see how it says one sample T? We're doing a two sample T. And the first guy was men, and men, what did we have in men? We have 28 was the mean. The standard deviation for men was 2.9. And guess what? After me telling you all that hard work about how to calculate degrees of freedom, do you see here, you just type it in? No, you just type in the sample size. Oh yeah, it was something to do. And it'll figure out what the degrees of freedom are for you. And then the second one, which is women, was 25. And the standard deviation for the women was also 2.9. And the sample size here was a little bit larger, 112. We're going to click on confidence interval. And they want a 95, which is good. Now, we've talked about this before. Remember, assume equal variance. If they say the data has been pulled, check it. If they say the data has not been pulled or unpulled, leave it alone. If they don't mention it either way, leave it alone, right? So the rule is going to be, unless they specifically say the data has been pulled, just leave it blank. That's now going to generate results. And there's lots of things there, but the guys that we are interested in is the lower and the upper. So I'm rounding these off to 1 decimal place. So it's 2.1 to 3.9. Now there's lots of other stuff in here. For instance, there's the standard error for each one separately. You might think, how did that degree of freedom turn into that weird number? Why isn't it, what would it be? 184. Why is it not 183? Why is it 151? The rule that I gave you for calculating the degrees of freedom is the combined data take away 1, right? But that's a very crude calculation for when you put two samples together. I think I've mentioned it before. There is some ridiculously ugly formula that you use when you're being more realistic about this thing called degrees of freedom. I'm not even going to go look in it in the book. You'll take one look at it and turn the page, right? So we just say, okay, that's the answer, and that's what it is. So we're done. Let's have a look at that data and see if there's any conclusions. Is this interval statistically significant that men's feet are bigger than women? Great. If you wanted to be more specific, aren't men's feet on average about 2 inches bigger than women? At least 2 inches, but not more than 4. Whatever use that would be, and I can't think of one. Well, I guess if you're making shoes for men and women, won't you probably make shoes a bit bigger for men? You know, more larger sizes. That's about the only use I could have of that. Okay. Next question I'm going to show you. It uses salt. And this is question 12. I hope you're all looking at 12. Right, okay. So 76 students in a stats class use their non-dominant hand. Oh, it's a little bit different. So I'm a right-handed person. So you take your left hand and you print letters of the alphabet in 15 seconds, right? And you see how many you get done. So I guess that could be a measure of dexterity, you know, more you get done. This is what they found. Oh, of course, they're going to separate males from females. 33 females, about 12.5 standard deviation. Standard error, I mean, we don't really need that number at all. It's there, but we don't use it. And the guys that we're going to use are these 6 here, aren't they? And we're going to eventually collect certain things. So let's see what they're asking us to find. Find the pooled standard deviation. Right. So I'm going to have to write these numbers down. So the females are going to be first. So N1 is 33, X1 bar is 12.55, and S1 is 4.01. And then the males are 43. The mean is 13.65, and the standard deviation was 4.46. Okay, I got all that stuff. And the first thing we're going to do is find SP, the pooled standard deviation. So click on this fella and to sample. Put in the women first, so that's going to be 33. Standard deviation was, no, get that in the right size. It's 12.55 was the mean. Then the standard deviation was 4.01. And then the sample size was 33. And then you go here and you do a sample mean of 13.65. And standard deviation is 4.46. And sample size was 43. And we're going to do a confidence interval. And they said they pulled the data, at least in the first one. And so I'm going to do that. But they're not asking us for the interval. They're asking us for the standard, the combined standard thing. So I should be able to generate results. And there's your answer. Now, if it's not pulled, right, remember that 0.988, right? Do you see how it's now 0.97? Right, instead of 0.988, it's 0.974. Do you see there's a tiny difference between the two? Right. If you pull it or you don't. So that was pretty much that. And what would the degrees of freedom be? Well, if you assume equal variance and you generate the results, can you see the degrees of freedom are 74? Okay. Put your last name down. We'll call it a day.